Hello everyone. Thank you for being interested in our project. The topic of our work is seismogenic and tremogenic slow slip near the stability transition of frictional sliding. Let's talk about the terms first. Slow earthquakes and slow slip events are two different phenomena, but they all occur together at the down dip of the seismogenic zones. The slow earthquake family, which includes tremors, low-frequency earthquakes, aka LFEs, and very low-frequency earthquakes, VLFEs, are seismic phenomena. They last about minutes to hours, and they generate seismic waves, so they can be recorded by seismic stations. Compared to them, the SSEs are much slower. They have slip velocities that comparable to plate motion, so they aren't able to emit seismic waves. They are considered as GPS observations as they can only be recorded by geodetic instruments. Despite the truth that SSEs and slow earthquakes have very different characteristics, but they are mechanically coupled, as they always happen at the same time and same place. Here we show the examples of the subduction zones, including Nankai Trough in Japan and Cascadia in the US. We also show the example of a major strike-slip fault, the San Andreas Fault in Southern California. The black dots on the figures show the sources of the slow earthquakes, and the color patches show the SSEs. We can tell that they are highly correlated. Here comes the introduction of the friction framework of our simulations. We apply the so-called multiplicative form of a friction law, and it acts similar to the radiant state friction law here. The same, we have the A smaller than B indicating the velocity weakening condition, and A larger than B indicating the velocity strengthening condition. L represents the characteristic weakening distance, and it is a very important parameter that controls the rupture styles. And the state variable evolves the same with the radiant state variable. Here we also want to introduce two we called Dieterich-Ruiner Rice numbers, Ru and Rb. Assume other parameters are fixed. Ru is determined by the L, and it controls the complexity of the ruptures. So here I put two examples to explain the effect of Ru. The x-axes are distance of the fault, and the y-axis are time steps. The left figure shows the sleep cycles of a small Ru regime. You can tell that it generates simple aseismic periodic SSEs. The right side shows the sleep cycles of a large Ru regime. It generates complex earthquake sequences. The other number, Rb, reflects the velocity dependence. Positive Rb represent velocity weakening and negative Rb represent velocity strengthening. Now let's go back to the topic of concurrent slow and fast ruptures. So the physics underlying this concurrency is still unresolved because first, aseismic and seismic ruptures of radiant state dependent friction faults are mutually exclusive. As I showed, slow ruptures are outcomes of small Ru regime, and fast ruptures are generated by large Ru regime. And second, the parameter space that produces SSEs is narrow. So I put 8 scenarios here with a slightly increased Ru. We see that the SSEs can only be generated by two parameter set, Ru equals 1.75 and 1.8. So it cannot explain why the SSEs are very common in different subduction zones and strike-slip faults. Last, the SSEs produced in this parameter range is aseismic, which is conflict with the coincidence of tremors and SSEs. Here we propose a physical model to solve this problem. And we argue that this kind of concurrency of SSEs and slow earthquakes are the natural response of the transition between velocity weakening and velocity strengthening. In other words, RB approaches zero from the positive side. People also found that there is a low permeable seal covers this region and causes overpressure. So we also apply decreased effective normal stress to mimic this environment. Here are the parameters that we used for our simulations. We use a 2D antiplane model. This mechanism is for strike-slip faults, but we believe it is enough to explain the physics well. And the fault is 20 kilometers long, including the 5-kilometer velocity weakening area, and we use a quasi-dynamic approach. Other important parameters are effective normal stress is 20 megapascal for our cases compared to commonly used 100 megapascal for crustal faults. And the RB number ranges from 0.02 to 0.5 since we want to explore the near neutral to strong weakening condition. And the RU number ranges from 1 to 220 to conduct the parametric space of RU and RB. Here, the left figure is the RU-RB parametric space. Again, the x-axis RU controls the complexity, and the y-axis RB reflects the velocity dependence. So smaller RB here represents near neutral conditions, and larger RB is the typical velocity weakening friction. The background color here is the peak slip velocity of the rupture cycles. And the whole space can be divided into 5 subspaces. The very left domain is the stable creeping, which is accommodated when RU is around 1. So next to the creep subdomain, there is a thin area. We call it creep waves, or the waves of partial coupling. This behavior describes a specific kind of creep, when the creep velocity can sometimes be slower or faster. So they are basically very long-term slow-slip events with no gap between two cycles. Then the next subdomain is yellowish, meaning that the event's peak slip velocity is not in seismic range. So this area is the aseismic slow slip events. And this kind of slow slip events can be generated by typical RB, but small RU, like panel C shows, or by relatively larger RU with a near neutral RB, like panel D shows. Then the huge red domain at the upper right of the phase diagram represents the earthquakes. But the bottom right corner represents another kind of slow slip events, the seismogenic slow slip events. So you can't tell the difference between the seismogenic SSEs and earthquakes based on their peak slip velocity, because this kind of SSE is seismogenic, meaning that their peak slip velocity is high. But when we look at the cycles from panel E, the earthquakes, and panel F to I, the seismogenic slow slip events, the behaviors are quite different. So this kind of SSE is basically fast subruptures embedded in slow ruptures. In other words, this is a mix-up of fast and slow ruptures. And this kind of behavior can only be explained by a near-neutral frictional condition, or RB approaches zero, and large RU number. Here, our RU is bounded because of numerical limitation, but it can be arbitrarily large, which explains that why SSEs are very common at the down-dip extension of the seismogenic zones. Because in this frictional transition zone, the parametric range to generate SSE is large. However, the seismogenic slow slip events aren't able to explain tremors, as tremor phenomena is a specific seismic behavior, which is a burst of seismic signals. So we design a heterogeneous model with small-scale velocity weakening asperities within the near-neutral region. And this model is able to generate clusters of rupture velocity peaks, which is similar to observed tremors, as figure A shows here. Here we can clearly see that the SSEs become much more complex using the heterogeneous model, with a lot of subrupture branches. And the tremor-like activities are triggered when the rupture front of the SSEs pass the asperities. Then the tremors perturb the stress field and causing more secondary rupture fronts of SSEs and result in more tremors. So this result has the potential to explain some tremor characteristics like stationary and rapid tremor migration. We then convert the time steps to time to show how clustered these tiny fast events are. The histogram shows the density of the events in time, and there is one seismic active period for some of the events. And these periods are very short, like minutes to hours, so the fast events are highly clustered in time. When we look at these active time periods, as panel C to E shows, the interaction of slow slip events and tremors, meaning that they trigger each other, are more clear. So in order to make sure the fast and slow events that we simulated can be observed by some kinds of instruments, we also simulate the GPS and seismic data. We have a dipping fault here, and we have a we call seismogeodetic station right at the east of the hypocenter, because this station can only receive S wave due to the radiation pattern, and it simplifies our analysis. So the upper panel of figure B shows the GPS data, and the SSEs are clearly recorded. And the lower panel is the simulated seismograms. And we can tell that the seismic signals are more active during SSEs, even though it is hard to distinguish the arrival due to the clustering of the fast events in time. We also choose one seismically active period and set up a set of seismic stations with the same azimuthal angle to observe the move-out effect of the seismic phases. So the angle is different from the seismogeodetic station, as now we want to see both P and S waves here. Some of the body wave phases are identifiable, but most of them are hard to distinguish because they are too close to each other and the arrivals overlap. Then we choose one set of events, and we also set up a seismic station set which contains 16 stations with the same azimuthal angle. And here we use a different azimuthal angle with the seismogeodetic station because we don't want to see both P and S waves to check the move out effect. And here we can clearly tell that the three foreshocks and the main shock has very clear P and S arrivals. But the following potential tremors, we can't really tell the arrivals because these events are too close in time and location. We believe that's a nice indication that tremors represent the chatter from tiny distributed sources. So here comes our conclusion. Seismogenic slow slip events take place on near neutral velocity weakening fault. And slow slip events take place for a wide range of characteristic weakening distance. The conditions met below the seismogenic zone can explain co-located fast and slow slip. Tremor-like seismic events occur when slow slip rupture fronts traverse heterogeneities. Thank you again for your time, and please contact me anytime if you have questions or comments about our project.